Okay, folks, let's get started. Feels a little sparse in here. Is there like an event going on?
It's cold outside.
It's cold outside? Okay, well. All right, I guess they missed the fun. How's Boids going for folks? It seems to be going relatively smoothly. I've seen a number of groups with a single Boid flying around, which is good, and a couple of groups with small but well-behaved flocks. I wanted to just very briefly mention a couple of bugs that I'm seeing in a number of different groups so that you can remember these things and keep an eye on them. One is to remember that we're keeping track of our Boid position and velocity using fixed point. And there's a section of the algorithm which you're all asked to implement this week, which is speed checking, which involves a division by the present speed of the Boid. You're renormalizing by the Boid's existing speed. Remember that that division requires that you do a fixed point division for which there will be a macro at the top of your demo code. So a relatively common error that I'm seeing is to use the divide symbol instead of the fixed point macro for division. And the consequence of that is, I think, stationary Boids. I think that's the bug that we see. Another common bug that I'm seeing is just to remember that the other parameters associated with this algorithm, things like the turn factor and the centering factor and all these sorts of things, those are given to you in the write-up in a decimal value. Just remember that you need to translate that to a fixed point value. And when you do so, suppose you're initializing some fixed point. Suppose you're initializing the turn factor, right? And you say, okay, fix 15 turn factor equals, and you want to give it the initial value. If you just type 0.2 and you don't do float to fix of 0.2, it will do I believe it does an implicit cast to a signed int, and it just makes it 0. So the bug associated with forgetting to do a float to fix on your turn factor is you start the animation and the Boids just fly off the screen and never come home because your turn factor is effectively 0. So they leave the margin. You start applying the turn factor, but you're adding and subtracting 0 from each of their velocities, so they just keep on flying away. Any other bugs that folks want to talk about? Okay, I'll just remind you gently once again that it is a good idea to be thoughtful about the order in which you implement this algorithm so that you can test whether a part of it is working before you add the next part. There's a lot going on here, and because it ends up being sort of a complicated emergent phenomena, diagnosing bugs can be a little bit tricky here. So it's a good idea to, for instance, start with just turning around at the edges of the screens and get a bunch of Boids that don't know anything about each other, just flying around and turning around at the edges. And then maybe add alignment. So now, okay, you have a bunch of Boids flying around, and also if they're in each other's visual range, they try to align with one another. And then maybe you add cohesion. And you could test if that's working by turning the centering factor up a bit high and see if they sort of aggregate. Right? So you can go through this exercise of adding one of the contributions to the velocity update, asking yourself, what is the emergent effect that I expect to see in the limit here? If I make this really extreme, how should I see the flock behave? Do that test, see if it behaves as you expect, and then add the next thing in. Yeah?
Would we be able to do like an approximation of a visual like range, or does it have to be like exact?
An approximation of what variety?
Like if, because I think you said like square roots and like divisions, not as much, but like can be very expensive operations. So if we could find some like, I don't know, way to approximate that using only like addition and subtraction, like shifting.
Yeah, that sounds like a good cheating opportunity. Yeah, a cheating of the okay variety. Yeah, what if your visual range was described by some shape other than a circle? Is there another shape for a visual range that you might be able to compute more quickly? I think so. Yeah, something maybe rectilinear. Okay, so what I want to do today is, first of all, go over the plan for the next like week and a half or so. So in Lab 2, as you're all aware, Lab 2 is purely a computer graphics animation lab, and the only piece of external hardware with which you're interacting in Lab 2 is the VGA screen. And in Lab 1, you will have gotten some practice with using the provided VGA driver library. So you're familiar with this point, at least somewhat, about making stuff happen on the VGA screen. We haven't yet talked about how that VGA driver actually works. And in Lab 2, because we have less other peripherals to introduce than we do in Lab 1, it's sort of an opportunity to pop down a level of abstraction and maybe talk a little bit about how things like the VGA driver are actually implemented, which is useful for two reasons. It's useful, first of all, because as I've talked about a few times in this class, a class like this, the eternal question is, what do we hide and what do we reveal to the students? What's abstracted away and where are we asking for you to, at what level of abstraction are we asking for you to work? And whenever a level of abstraction is hidden, it's good to know what's hidden, because that helps inform your debugging. So we talked about with the SDK, right? The SDK under the hood is just doing register manipulations. If you internalize that, then it makes it a whole lot easier to debug SDK function calls, right? Because you can go in and see what it's actually doing. And the same is true of this VGA driver. The thing that the VGA driver is abstracting away from you is a state machine running on these PIO coprocessors that I've alluded to a few times. I wanted to talk about what this PIO subsystem is. It's entirely unique to the RP2040. It's really, really interesting. So I want you to know about it. Because it's unique to the RP2040, it felt to me, so because I find this so interesting, I was highly tempted to come up with some lab that asked for you guys to do something with this, but it felt maybe just a little bit niche for a microcontrollers course. If this were an RP2040 class, then okay. But because this is a microcontrollers class that uses the RP2040, it felt like maybe devoting a whole lab to this thing wasn't quite right for this course. But I cannot resist the temptation to at least talk about it. And the other reason that you'll want to pay attention to this is if you want to get the most Boids that you can in Lab 2, you will have to modify the VGA driver a little bit, which means that you will actually have to go into the PIO programs that are in that VGA driver and do a little bit of manipulation. Not much is required. In fact, very, very little is required. But in order to make the appropriate changes, you have to at least have some understanding of how this is working. So my plan for the next about week and a half is to start each lecture going over any bugs that folks want to go over associated with Boids. And if I notice some common bugs, then we'll go over that. And then to spend the remaining time using this next week and a half or so as an opportunity to pop down a level of abstraction and pull back the curtain on how some of this stuff is working under the hood. And by the way, the next two lectures after this one are going to be slightly odd. So on Monday, we're going to have a guest lecture from Mason Peck. Folks familiar with him? Some people. So Mason is a professor in mechanical and aerospace engineering. He happens to be the person that I did my PhD with. He is an expert in spacecraft engineering. So his research, he researches a number of different things, but it's his research that sort of inspires Lab 3. He's one of the world's leading experts on spacecraft attitude control. Attitude being the technical term for pointing a spacecraft in the direction that you want for it to point, using things like reaction wheels, which we're going to use in Lab 3. He was also the CTO of NASA for 2 years, and in that time, he helped steer the direction, the technical direction that the whole NASA agency took. And so he's going to come and talk about whatever he wants to talk about, really. But what I've gently requested is that he talk about electronics in space. So supposing that we wanted to take one of our microcontrollers projects and put it in a spacecraft and take it up into orbit, what has to change? What's different about the design process when you're designing for a spacecraft, a microcontroller real-time system for a spacecraft? What has to be different? And what are the different sets of risks that are posed to electronics in space as opposed to in our lab? And how do we design electronics to survive those risks? Things like potentially wild thermal swings or really, really heavy radiation exposure, stuff like this. What are the mitigating strategies that we use? So the whole lecture is entirely related to the content, but a little bit tangential. I just thought it would be very interesting to hear this sort of stuff. And then the Wednesday lecture is going to be recorded. The reason for this is I'm doing a microcontrollers flavored trip early next week, which I thought a lot about because as a student, I always thought it was kind of uncool for folks to do this in the middle of the semester. So I thought a lot about it, and I'm going to do a Monday to Wednesday trip. I'll be back by the Wednesday evening lab section. So I will only miss the Wednesday afternoon lab section, but you'll be in good hands. Incidentally, the trip that I'm doing is, have folks heard of this company SpinLaunch? Okay, so just because I feel like I need to justify this to you. SpinLaunch is this company that has built this crazy piece of infrastructure out in the desert of New Mexico, right outside of the White Sands Missile Range, a place called Spaceport America.
Can I come with?
What's that?
Can I come with you?
So this is a very, very large centrifuge. It stands about as tall as the Statue of Liberty. And what they do is there is a little arm in here that spins around at truly epic speeds. They pull a hard vacuum on this whole thing and then spin an arm in here at unbelievable speeds, and they put a little payload at the end of that arm, and then they time the release of that payload exactly right to shoot it out the top of this centrifuge here. And the notion is that what they're trying to do is build a device that can replace the first stage of a rocket. So anytime you launch a spacecraft into orbit, every rocket that has ever gone to orbit has been at least 2 stages. One part of the rocket that gets you basically above the atmosphere, you drop that, you turn on the next rocket, and that gets you into orbit. The notion is that an even larger version of this could ultimately replace the first stage of that rocket. So you put your satellite into this thing, spin the hell out of it, and let go. It shoots it above the atmosphere. Then you turn on your second stage, and it goes. So what they've built is a suborbital accelerator, which will get stuff not into orbit, but up above the atmosphere. Whatever they launch has to be able to survive 10,000, a lot of Gs, over tens of thousands of Gs getting spun like this for a long time and get shot out. So there's not a lot of stuff that can survive that sort of loading, but printed circuit boards are pretty good, actually. Solid state electronics are pretty good at this. So as some of you are aware, I spent my graduate work working on these little printed circuit boards that were spacecraft, And so I sent a few of them out there, and on Tuesday, we're going to put a handful of these things in this suborbital accelerator and shoot them out the top up into space. And it's just too bizarre for me not to go. It's exciting for me for a few reasons. I spent a lot of time working on these things, and the thought of seeing them blast at Mach whatever out the top of this centrifuge and up towards space just makes me really happy, and I want to see that happen. And then the other exciting aspect of this trip is that hopefully it could lead to some MEng projects, designing other sorts of payloads for putting into this vehicle. So it's productive for that reason too, I think. But in any case, that's where I'll be, but I'll be gone for the Monday lecture, which will be a guest lecture. Wednesdays will be recorded. I will be back by Wednesday evening. Yeah.
Do you have to put your circuit boards into like a capsule of some kind?
Yeah, which is all designed by them.
Does the capsule have like testing on it to like see how many Gs it does sustain, and like how hot it is?
I'm sure. I don't know the details of this. Hopefully I'll be able to report back to you after next week a little bit more about how all this works. Okay. So anyway, that's the plan for the next week and for the next couple of lectures. So I think you'll really enjoy the guest lecture by Mason. So, unless there are any further questions, I want to start talking about these PIO coprocessors, the programmable I/O subsystem on the RP2040. And let me just state that because this is an entirely unique feature of the RP2040, the best way to teach it isn't obvious. So I'm going to take my best stab at sort of introducing this thing and talking about it. There's a lot to talk about with it. So my general approach is going to be to talk about it at a high level. What's it do and why is it useful? And then we'll look at sort of a schematic flowchart level of abstraction of what's going on in each of these PIO processors. And then talk about the set of instructions that you could give to each one of these and what they do. And then we'll look at some example programs and maybe iterate on this a few times And then ultimately, we'll look at the VGA driver as a particular example for an application of one of these PIO coprocessors that you all will have been working with, right? And we'll talk about how you might consider modifying that to increase the number of boards that you could get. So let me start by just reminding you again of this picture. This is from chapter 1 of the RP2040 datasheet, and it's showing all the stuff that's in the RP2040. A lot of this stuff we've actually already talked about a little bit or a lot. So there's the two processors up here. They share a bunch of interrupts. They both talked about SIO. We've talked a bit about DMA. And I'm just reminding you that there are two PIO coprocessors in here. And this is what I want to talk about today, is these things here. The green color, incidentally, is just to remind you that these have a direct connection to all of the GPIO ports. So you can control all the GPIOs from these coprocessors, in addition to being able to control them from the ARMs if you wanted to. So there are a few levels of abstractions here. What I would like to do now is consider one of these PIO coprocessors and consider the stuff that's contained within one of those PIO coprocessors. So each PIO block, it's called, there's two PIO blocks, can contain up to 4 state machines. You can think about a state machine as being a program that lives on this particular PIO block. Those programs may be entirely independent from one another, or there do exist mechanisms for signaling between state machines on a single PIO block, and we'll talk through some of those signaling mechanisms. So it may be the case, for instance, that state machine 1 is just doing its own thing, perhaps manipulating a set of GPIO ports, communicating some information back to the ARM via a DMA channel. Or it may be the case that state machine 1 and state machine 2 are sort of working together. State machine 1 does some stuff and then signals state machine 2 to run a set of instructions, and then state machine 2 may signal back to state machine 1. So 4 programs, all of which can be entirely independent, but that also do have a mechanism for signaling among one another. On a single PIO block, this is true. So this whole image, you can imagine that there are sort of 2 of them in the RP2040, 1 for each of those 2 PIO blocks. So each of these state machines represents a PIO program, and we'll talk about what exactly that program looks like, but it is written in assembly. There's an assembly language with which you program these PIO coprocessors. There's 9 instructions, only 9 instructions. We'll talk through what those instructions are and how they work. All 4 state machines on a particular PIO block share the same instruction memory. So all the instructions that describe one of these state machine programs, they all live in the same instruction memory. And the total number of instructions summed across all 4 state machines on a particular PIO block may not exceed 32. So that's a fun constraint. So you may not write any program for a particular PIO block that exceeds 32 instructions. And that 32 instructions can be distributed among all 4 state machines, but the total number of instructions may not exceed 32. And then in order for this to be useful, right, these programs that are running, they have to be able to communicate to both the outside world and back to the processors, right? So to communicate to the outside world, each state machine has direct access to all the GPIO ports. So you could have a particular state machine toggling all 30 GPIO ports just as fast as it wants. And then likewise, each state machine connects to 2 FIFOs, the RX FIFO and the TX FIFO. And it's through these FIFOs that the state machine can communicate back to the processors, the ARM processors. And in particular, the ARM processors can go and access the information in these FIFOs directly. That's an option. The more common and more powerful mechanism of communication between these PIO processors and the ARM is to point a DMA channel at these FIFOs so that the DMA channel automatically, according to conditions that you tell it, it will go in and automatically extract data from the FIFO and move it over to memory so that the processor can do something with it. Or alternatively, if the state machine is sucking data in from one of these FIFOs to do something with, maybe put it out to the pins or do whatever it's going to do, You can configure a DMA channel to automatically move data from processor memory back into the FIFO when it empties. So that behind the scenes, you can have some state machine running that's maybe manipulating GPIO ports, writing them or reading them, and is being fed or is feeding these FIFOs that connect to DMA channels and back to the processor. So that you can have high bandwidth communication with no CPU interaction between the ARM and these PIO state machines. And the other mechanism by which these state machines can communicate back to the ARM is each is capable of throwing interrupts. So you could, for instance, ask for the state machine to do a series of instructions and then throw an interrupt, and that interrupt is visible to the ARM, and you could have an interrupt service routine written to respond to it that perhaps clears that interrupt and then restarts the PIO coprocessor if you so desired. Anything else I want to say about this at a high level? So what makes these so interesting is they are highly, highly specialized for I/O. So every one of the instructions that we'll take some time looking at today, those 9 instructions that you can write for any one of these state machines, every one of those instructions is guaranteed to execute in one cycle. Guaranteed, no questions. So if you say, well, we'll look at them all in a moment, but whatever instruction you write, it's guaranteed to execute in one cycle, which means you can write highly, highly deterministic programs for these PIO processors. What do I mean by a deterministic program? Well, we could take a look at a PIO program written in assembly. We could say, okay, when this program starts, it's going to be executing this instruction. I could ask you in 2,548,722 cycles which line will be executing, and you could tell me really quickly, because you know exactly which instruction is going to be executed on exactly which cycle. Now you can introduce delays, right? Like you can have a program wait to run until it's signaled by some process that's harder to predict, something that's running on the ARM. But you can have an independent PIO program that is completely deterministic. You know exactly what it's going to be doing on every single cycle. Programs like that, highly deterministic programs like that, are, for me at least, I typically only associate with things like FPGAs, right? So what makes this really powerful is your programs are highly deterministic. They can manipulate all 30 GPIO ports. They can communicate to the DMA channels, which can move up to 32 bits at a time per CPU tick. So it allows you to put together really, really high-speed digital interfaces. VGA is an example of this, right? As some of you may be aware, the clock line to a VGA screen is 25 megahertz. It's actually like 25.172 megahertz, but you can get away with 25. That's really fast, and we could perhaps set up a connection to a VGA screen on some other microcontroller without using the PIO ports, but it's going to probably cost us a lot of CPU time. So maybe we could get the microcontroller to talk to the VGA screen, but you're probably not going to get a ton of Boids because you're probably not going to have that much time left over after you're done doing all this communication with the VGA to do interesting graphic stuff. We offload all the communication to these PIO coprocessors, and we spend all of our CPU time doing graphics.
Is it running the same clock frequency as processor?
Yes. Yeah. So we'll talk about this. It is, unless you tell it not to, each of those instructions that executes once per cycle, that's once per CPU cycle. So that means at 125 megahertz out of the box. But each also has a clock divider so that you can say, I would like for each instruction to execute only once every 5 cycles. So you can slow down the PIO state machine relative to the processor if you want to. And in fact, the VGA driver does this. Because we want the data to go out at 25 megahertz and the clock is running at 125 megahertz, we slow it down so that our instructions are being executed at about a 25 megahertz rate. Anything else to say about? So just as another example of this, I've been working a bit with, do you guys know Professor Lal, Amit Lal. Okay, so you may or may not be aware that among many things, one of the things that he and his group are working on is this very interesting imager. It's like a camera that you can put your finger on, and it takes an ultra close-up picture of whatever thing is on top of the camera. Fingerprints, or they do very cool demos where they spray some isopropyl alcohol on the top of the thing, and you get really interesting patterns as it evaporates. In any case, they've been driving this device with an FPGA because the device requires a sequence of control inputs that have to all be timed relative to one another at 200 megahertz. It's usually an FPGA thing. And by the way, there's 30 control inputs to this thing. So we've gone through a lot of effort over the past couple of months of replacing that FPGA with an RP2040. The RP2040, we aren't really using the ARMs at all. The whole program that the RP2040 is running is all PIO programs communicating to DMA machines. But these PIO programs are generating all the control inputs to this imager, all 30 of them at 200 megahertz, and it works. They can get the image off of it, which is exciting because an FPGA is like $400 and these are $1, right? So it's really exciting. Okay, so this is a high-level view of what's going on in a particular PIO block. The next level of abstraction that I'd like to zoom into is one of these state machines. What's going on in one of these state machines? So, in any one of these machines, you have 4 registers. Each of these registers is 32 bits wide. You have an X scratch register and a Y scratch register. These are what they sound like. They're just places where you can store 32 bits of information whenever you want to. Maybe you want to increment a counter to time something, or maybe you want to just use it for storing some temporary value while you're doing arithmetic of some variety. Okay, so there's just scratch registers here where you can put stuff temporarily or use in whatever way that you want. You then have 2 other 32-bit wide registers called the output shift register and the input shift register. These communicate directly with those 2 FIFOs that communicate in and out of each PIO state machine. So in particular, the TX FIFO, the transmit FIFO, communicates to the output shift register. So as we'll see in a moment, there's a particular instruction, one of those 9 instructions that you can give to the PIO coprocessor is a pull command, which says, take whatever in the TX FIFO and move it over here into the output shift register. Likewise, there's an input shift register that communicates directly to the RX FIFO, and there's a similar command called push that says take whatever in the shift register and move it over to the RX FIFO. And remember that it's these that are sort of visible to things like DMA channels. And then the other interesting things that you can do with these input shift registers, and with the input shift register in particular, is you can say pull information into this register, and you get to specify where you'd like to get that information from. So you could say, please pull 2 bits from the pins. And then you read the pins, and the value of the pins, the digital value of the pins, appears in the input shift register for you to do whatever you want to do with. And likewise, from the output shift register, you can say, move the data that's contained in this register to some destination. And you get to specify the destination. The destination might be one of these the X scratch register, it might be the Y scratch register. You might move data into the shift register, or you might push it out to the pins. So you have 4 registers here. You have a connection to the GPIO ports. You have a connection to these FIFOs. There's also the program counter. This is keeping track of which instruction are we presently executing. There's a jump command that we'll talk about that modifies this program counter to move you from one instruction to some other instruction in your program conditionally. There's a clock divider, and then there's control logic. So there's not that much going on in these things, right? There's 4 registers. One of those registers connects to the TX FIFO. Another one of those registers connects to the RX FIFO. You have a connection out to the GPIO ports, in and out. That's about all that's going on in there. And the instructions that we'll look at, that set of 9 instructions, all that those are really doing is moving stuff around among these resources. You know, it moves stuff between the registers, it moves stuff from registers out to GPIO ports, it moves stuff from GPIO ports into registers. It allows for you to deterministically, in one cycle, move data from one place to another place. And, of course, to do, you know, apply some logic to it so that you're doing something intelligent with the data that's getting moved around. Okay. Questions about this? 4 registers, 2 FIFOs, GPIO ports. That's what we get to play with. So, what are the set of instructions that we can give to a PIO processor? What we'll see, we're going to look at some example programs here in a second, but when we look at a program, what we'll see essentially is a sequence of instructions that look like this. We're going to talk through each of them in detail, but let me just summarize them now. There's a jump instruction, which does maybe what it sounds like. It allows for you to, say, move the program counter to this particular part of the PIO program. So it allows for you to jump to somewhere else in your list of instructions. So you're going down, doing instruction, you hit a jump, it can evaluate whether some condition is true or not, and depending on its evaluation of that condition, it'll jump to somewhere else in the program. So it allows for you to do things, for instance, like execute a series of instructions and then jump back to the top, and execute that series of instructions again and jump back to the top. And it allows for you to do that some number of times and then move on and do something else. We'll see an example of this. But all that this is doing is moving your program counter to some other place in your program. There's a wait instruction. This says execute each of these instructions, and when you get to the wait until some condition is met. And we'll look at what those conditions can be. But you could, for instance, wait until some pin goes high. One of the physical GPIO pins. You could have your PIO program sit and wait, and then when a pin goes high, the rest of it executes. You can alternatively have it wait on what they call an interrupt. It's kind of more like a flag, really. But it's these interrupts that allow for signaling between state machines on a single PIO block. So you could say, I would like for the state machine 1 on PIO block 0 to go through and execute. It gets to this wait, and then it will wait until it is signaled by state machine 0, say, and then it'll continue on. So this allows for you to delay execution until some condition is met. There's an in command. This moves data from some source that you specify into the input shift register. So that might be the pins. You might say, go read all the pins, move the data that you find into the input shift register. It might be one of the other registers, okay? But it allows for you to get data from somewhere and put it into the input shift register so that you can then do something with it. Out moves data from your output shift register into the, or no, I'm sorry, it moves data, yes, from the output shift register to a specified destination. Maybe it's the pins, maybe it's somewhere else. Push will move data from your output shift register to the TX FIFO, RX FIFO. So to be received by the system. So whatever information is contained in your output shift register, this bumps it up into the FIFO. Pull moves data from the other FIFO into the input shift register. I know this is a lot of information quickly. We're going to go back through this, but I want to just sort of summarize them quickly first. Move does what you might think. It says, please move data from a specified source to a specified destination. Maybe you want to move data from the X scratch register to the pins. You can do that. IRQ, IRQ, or interrupt, this is a signaling mechanism. So it allows for you to signal from one state machine to another state machine. It also allows for you to signal back to the CPU if you cared to. You could have your PIO program throw an interrupt that is seen by the processor, and there could be an interrupt service routine associated with that. And then set allows for you to specify the value that you would like to have placed in, say, the X scratch register or the Y scratch register, or a configurable set of pins. The one caveat being that you have the size of the data payload is constrained to 5 bits. So each of these instructions is 16 bits wide. And what this table is showing us is what each of those bits means or represents. Let's just look at the data sheet quickly. So in the data sheet, all of chapter 3 is PIO. So let's just take a look. You'll see some familiar diagrams in here. And if we scroll down, we will find a description, a better description than I just gave of all of this stuff. So there's a description here of the output shift register. There's a description here of the input shift register. Shift counters. We can talk about this, but one of the interesting things that you can do is, actually, let me get to that in a second. I'll talk about that later. What I wanted to get down to was the instructions. And I wanted to talk through them in a little bit more detail and then look at some examples. So here's the table that we were just looking at. It contains all 9 instructions. And here is a more verbose description of each of those instructions. So for instance, the jump instruction. What this is telling us is that a jump instruction will look like jump, some condition, and then a target. So the condition is the condition under which you would like for the jump to occur, and the target is where you would like to jump to. So what are the conditions under which you can have your program jump? Well, you could have no condition, in which case you're executing, you get to this jump command with a specified target, and it just always goes to that target. Or alternatively, you could say, I would like for this program to jump only when the value in the X scratch register is 0. So maybe you are decrementing the value in the X scratch register somehow, and when it gets to 0, a jump occurs. It allows for that. Alternatively, you could have the jump occur when the X scratch register is non-zero. It will evaluate this condition and then decrement the value of the X scratch register after having evaluated it. So why is this useful? Maybe you have some section of code that you want to have executed, I don't know, 20 times, and then you want to move on to another set of code. You set the value of the X scratch register to 20. You go through the section of code that you want to have executed 20 times, at the bottom of which there will be a jump command, the condition being this one, X minus minus. It'll ask, is the X scratch register 0? If not, I'm going to jump back to the top of this collection, this set of code that I want to have executed 20 times. But also, if it's not, I'm going to decrement it. And then the 20th time that you come through, it'll say, is the value of the X scratch register 0? Oh, it is? Okay, then we just move past that jump command into the next part of the code. We'll see an example of this, but it allows for you to have a part of your PIO program run a specified number of times and then move on to another part of the program. Similar stuff for the Y scratch register, jump when Y is not 0, jump when Y is non-zero prior to decrement, just as before. You can have the jump condition being the X scratch register is not equal to the Y scratch register. And you can jump on the value on a pin. Only jump if this pin is high. And you can jump on whether or not the output shift register is empty. What you'll find is you kind of get your brain into a little bit of a different mode when you're working with these things, because it's highly constrained, but even within these constraints, there is enough freedom to do really complex stuff. Just with these very, very basic capabilities, you can put together really complex programs. Well, complex in the sense that they do complex things. The programs themselves will never exceed 32 instructions. So to the extent that length is a measure of complexity, they're rather simple, but they do complex things. Okay. The wait command. You can, so what does a wait command look like? A wait command looks like, it looks like wait and then polarity, which is to say wait until true or wait until false. And then what you would like to wait on. Do you want to wait on a GPIO? Do you want to wait on a pin? Do you want to wait on an interrupt? And then you specify which of those GPIOs or pins or interrupts you would like to wait on. Right, so wait, you could say wait 1, pin 1. And it would say, okay, wait here until pin 1 is asserted, until it goes high. You do the same thing with an interrupt, right? You say wait here until we receive an interrupt from either the CPU, the ARM, they can communicate this information, or from one of the other state machines. Okay, in allows for you to shift a specified number of bits from a specified source into your input shift register. And those specified sources from which you can get information, get bits, include the pins, the X scratch register, the Y scratch register, null, which is to say all zeros, the input shift register or the output shift register. And there is a shift counter in here that's keeping track of how many bits have we shifted into the input shift register. And you can configure your PIO state machine such that when it counts that a certain number of bits have been shifted into the input shift register, it automatically moves it to a FIFO to be received by a DMA channel and can start grabbing more data again. Okay, so this is for getting information from somewhere into the input shift register. And the command will look something like in, you specify the source, you specify the bit count. Out is very similar. You shift a specified count of bits out of the output shift register to a specified destination. And those destinations look really similar to the sources that are possible for the in command. Okay. Push, which moves data from your input shift register to the RX FIFO. Pull, which moves data from the TX FIFO into the output shift register, right? So you could have your TX FIFO, for instance, being fed by a DMA channel, and the DMA channel can have we talked about how we paste these DMA channels either using a timer or by using some sort of signal from a peripheral with which we're communicating. The TX FIFO can signal when it's empty to a DMA channel so that as soon as we have moved all the data out of that TX FIFO into the output shift register, maybe for ultimately being put out to the pins or something like that, we'll look at some point this week at a PIO-based implementation of a stepper motor driver, and that's approximately how that works. We can have the DMA channel automatically start its next transaction immediately when the TX FIFO empties, so that you're pulling data in from the TX FIFO. As soon as it empties, the DMA channel pops more data in there. Move command. Specify a source and a destination. It'll move whatever is at the source to wherever is in the destination. We're going to get to an example in a moment. I see people's eyes like, okay. And interrupt, which looks like IRC, interrupt number, and then there's some options here where you can say, for example, IRC wait interrupt number means, say you want to set interrupt 1 to be received by some other state machine. This says set interrupt 1 and then pause on this line until that interrupt is cleared by the other state machine. So it's a method of synchronization between state machines. And then set is perhaps rather simple, but it allows for you to specify some data that you would like written to a destination. So you could write data to the pins, the X scratch register, the Y scratch register, and so on. Okay, and that's it. Those are all the instructions you get. So as you can see, all that this is doing is allowing you various options for moving data from one of these registers to another one of these registers, from the registers to the pins, from the pins to the registers, from the FIFOs to the registers, registers to the FIFOs. The FIFOs you can plug a DMA channel into. And then there's some options here for doing clever things that control which instructions are being executed when. You've got things like jump options, right, which allow for you to conditionally move what's executing to somewhere else based on data that it sees or based on the condition of the GPIO pins. So let's look at a program. I'll just briefly mention that in addition to the assembler program that you write, you also have some configurations of that program that you can make. For instance, you can configure that clock divider that I was talking about, so you can have your PIO program run as fast as the system clock. So that means for all of you, 125 megahertz. If you were to overclock the CPU to 250 megahertz, then your PIO state machines would also run at 250 megahertz. You can configure auto push and auto pull, which is to say that if that shift counter realizes that it has moved all information out of, say, the output shift register, it'll automatically pull more data from the FIFO into that register. It saves you a pull command, right? So one of the things that you have to optimize for is the number of instructions, because you only have 32. So this allows for you to, in some circumstances, eliminate a push command or a pull command that moves data from your state machine out to the FIFOs or moves data from the FIFOs into your state machines. You can do FIFO joining. So if you're writing a state machine that you're only ever going to be sending data into, so you're never going to use the FIFOs that come in the other direction, you can say, okay, instead of having a 4-sample deep 32-bit wide FIFO in each direction, I'd like to chain those and have a single 8-sample deep 32-bit wide FIFO going in one direction. And so you can stack the two FIFOs to any state machine together. You are allowed to specify the pin mapping. So if you call a set command and you say, I would like to move this data to this particular destination, and you specify that the destination that you would like the data to be moved to as the pins, you configure which pins you're talking about. So the set command can move data to the pins. The out command can move data to the pins, and there's another one. And they are each independently mapped. The side set can also, we haven't talked about that, that can also move data to the pins. They're each individually mapped, and they can be overlapping. So you could have, for instance, the set command configure the same set of pins that the out command is configuring. Which could be useful. And this I'll talk about in just a moment. The side set, I'll just briefly mention, is each of those instructions, as I mentioned, they are guaranteed to execute in a single cycle. What's kind of amazing about this is if you think about something like the jump command, you can execute a jump, evaluate a condition. This side set option allows for you to also simultaneously set or clear some set of GPIO ports, and you can impose a specified delay all in the same cycle. I don't know how that works. I don't know how that works. Okay, so let's look at some examples. These are two examples of relatively simple PIO programs. This one I thought would be kind of nice to talk about because we just recently talked about the UART protocol, right? So this is a PIO program that is implementing, what time are we at? Oh, this is time. Sorry, okay, we'll talk about this next time. Consider reading about this, all right? I know that this was a lot of information. The strategy is going to be, you've seen the information once now. That's the worst part, right, is seeing it once. What I want to do now is go back and reinforce that with actual examples. And I think that this will add some clarity as we go. But please consider reading chapter 3 of the data sheet.